Am I audible?
Yes, sir, you are audible.
Okay. So till now we have seen some basic dynamic examples, and we try to write down the equations of motion for them, and then we try to simulate the result also. So now let us now go back and review some basic things related to the laws of the mechanics. These will be some basic features. We will develop some notions and representations so that we can solve some more interesting problems of dynamics. So is this figure visible?
Yes, sir, it is visible.
Okay. So basically now we will be dealing with the n number of objects, point objects. Till now what there was only one single object, and that too was a point object. But now the physical thing, the realistic thing, that will not be a point object, that might be an extended object. How we will be applying the Newton's laws of motion to that thing? And so we don't have Newton's law for the extended objects. We have Newton's law for the point particle only. And the second thing is that we have developed some notion. We have seen that if we can somehow represent the motion or the acceleration and velocity of the particle as a function of time and as a function of position, we can predict the future trajectory of the particle. So you can assume you may argue that if we have extended body, we have some extended body, so we can consider it as a n number of individual point masses, and then we can individually apply the Newton's second law, and uh, we can get the future state of the whole body. So some, but the thing is that you can think it like this. For example, we have some, say we have um, 12 grams of carbon, and this is some, there is some extended body which has a mass of 12 and it is made up of carbon. So in 12 grams of carbon, we know that it corresponds to 1 mole of carbon, and that is 6.023 in 10 to the power 23 carbon
Yes.
atom. Now, if you are applying some force, that means you are applying on force on these 6.023 in 10 to the power
One more.
23 particles. And these, yeah, Avogadro number of particles. So each particle, you will be writing the equation for its displacement for velocity and acceleration. So basically you have at least three variables in your z vector. We know what z vector. Z vector always contains the position vector, that is r. It contains the velocity vector and it contains the acceleration vector. So for each
Acceleration rate.
particle, you have three variables. Now think, you have 6.023 into 10 to the power 23 particles. So to each particle, with each particle we have three variables. So
Three.
we have three mole number of equations. So you have to integrate three mole number of equations to get the dynamics of 12 gram carbon, which is which is not feasible and which is not a practical thing, because you will be needing such tremendous amount of calculations and computations. So there will be a huge load on the computation. So that is why we will be extracting uh, some bigger picture of these things. That is the motto of today's lecture. So how we will be dealing with such problems. Uh, Although they are looking that we might be applying the same policy or the same trick which we were applying, but this is not how it will work. And I have already mentioned the problem with it. So let's assume that we have n number of particles. This is first particle, second, third, fourth, and n particles here. And out of these n particles, I have a particle which I have named as ith particle. This is iota. And I have taken a reference frame that is X, O, Y, and O is the origin for that reference frame. And I have taken some reference point C. Oh, this is not something, some particle, but this is
It's not
just
body.
this is just for reference purpose. Yeah, this is in this frame, and I am calling this as reference point C. So now I am defining a vector from O to ith particle as Ri and O to C as Rc. Then you can define a vector from C to I, which connects C and I and pointing towards I as Ri with respect to C. So we have Rc and I have denoted as Rc with respect to O, which I can also write as R of C with respect to O. See the notation, because you will be following these notations throughout the rest of the course. Similarly, I have Ri, that is position vector of this I with respect to the origin, and I can write it as RIO. Similarly, we have Ri with respect to C, I can write it as Ri with respect to C. See, there is difference when I write like this and when I write like this. Here I am writing I first and then slash C. And here I am writing RIC, that is R position vector of I with respect to C, and which by definition is Ri minus RC.
Sir,
Okay.
R I with respect to C, it should be it should be like RIC, position vector of ith particle with respect to C.
Yeah.
Second one, sir.
Yeah.
RCI.
Yeah. This
Why this,
is
sir?
how you will be
RC.
reading it. R, that is position vector of I with respect to C. R of I with respect to C.
With respect to C.
This is not R of C with respect to I. No, that is this notation. That is why I am saying this is how I am defining it. Okay, you can also define RIC and then read it at R with respect to C. But how I am defining it is that R of I with respect to C. Okay, this is just a notation. You can have different notation. But since I am your instructor, so you have to follow my notation so that there is no ambiguity in this. Okay.
Actually, sir, you have used the RCO, RIO, and then I think you should use RIC. RCO, relative
Yeah.
position of
R.
C with respect to O.
Okay. This is R of C with respect to and C. R
With
of C with respect to.
OC.
That is similarly here. I am writing R of I with respect to C and C. R of I with respect to C.
Okay.
These are in. These are consistent.
Ah,
This and
okay, okay. Yes, sir. Acha, acha, yes, sir. This is constant with this. Yes, yes. Okay, okay.
okay.
Now I got. Okay.
Okay. Now we have some postulates. One thing is that F external on some ith particle is nothing but mass of ith particle into acceleration. And we know this. This is what Newton's second law tells us. This holds for each particle. And the second one is that force on each particle can be written as some internal force plus some external force. So out of this, we are considering our system as these n number of particles. So for example, we are taking this ith particle. There will be some force which might be, for example, gravitational force, which is not because of this n number of n minus one number of particles, but that is something which is external to this system. That force which is acting on this ith particle, that will be considered as F external acting on this ith particle. Also, for example, let there is some wind. So due to wind, there is some drag force acting on this ith particle, and that force will also be external because that is not due to the system which we are considering. So depending upon the system, what you define as the system, there will be internal and external force on each of the particle. So that is what I am saying, that force on each ith particle can be broken down into two. That is F internal and F external on the ith particle. And the third postulate is that sum of Fi internal, that is, if you take all the internal forces, for example, there is some internal net internal force acting on this ith particle due to other. For example, that is pointing in this direction. And similarly, then there is this particle, and there is some net internal force acting on that particle, and that is this. Similarly, on this. So when you add up all these internal forces acting on the different particles of the system, you will find that the the sum of the internal forces summed over all the particles will be equal to zero. This is something related to action reaction forces. If uh, something is being pulled, it will pull the other system by the same force. So this is action reaction pair. And the fourth postulate is that Ri with respect to C cross Fi internal is equal to zero. So this is a little bit, we will get to this also when we will be dealing with the moment. But at this stage, let us see what I am saying. So RIC is this vector, and Fi internal is the internal force which is acting on this. So if you multiple this vector cross with F internal, similarly then you define another vector, and there will be some internal force, and similarly. So basically what you are doing, you are trying to calculate the uh, if you are making the cross product of this vector into F internal. So that is basically the torque acting on this ith particle about the point C due to the internal forces. Similarly, when you are taking the cross product of this vector multiplied by the internal. Hello?
Yes, Magle. Actually, sir, net was gone. So, sorry.
Okay, you can mute yourself, and when there is any question, you can unmute and ask.
Okay, okay, sir.
Okay. Okay, so is this clear till now?
Sir, can you repeat, sir? Last 2 minutes, actually, sir, there was interruption in the net, sir.
Okay.
So I have rejoined this.
Okay. So I was saying that this fourth, so basically from this fourth postulate, third postulate is okay. That is sum of internal forces is zero.
Yes, sir, it is sir, clear.
Okay. So now going to fourth one. So what fourth one is that RIC cross F internal is equal to zero. So what I am saying, so let the page refresh. I think it is still here. I am. Is my page got? Oh, okay. Now it is scrolling down now.
Yes, sir, it is scrolling down.
The whole page is now visible. Yeah.
Yeah, the whole page is visible.
Okay. So what fourth postulate says is that Ri with respect to C, that is position vector of this ith particle with respect to this reference point, that is this vector, crossed with Fi internal. So see, there the net force acting on this ith particle can be broken into Fi internal and Fi external. So if you take only the Fi internal, let us think that Fi internal is in this direction. That Fi internal is actually the force acting on this ith particle due to all other particles. And let us assume that is acting in this direction. So you are taking the cross product of this vector crossed with this F internal. Similarly, you will define this vector as Fi with respect to c for this particle, and then there will be some internal force on that this particle also. Let us assume that is in this. You take the cross product of that. Similarly, you do it for the whole system. You take each particle and you take its position vector with respect to c, and you take the internal force acting on that particle. You take the cross product, add over the all the particles, and you will get zero. This is what this fourth statement is. And you know this R cross F is actually nothing. It is the moment of the internal force about C on this ith particle. So that means the internal moment summed over all the particles about some reference point is zero, no matter what this reference point is. Irrespective of what the reference point you are choosing, this torque will or the moment will be zero. So this doesn't depend upon the C. So these are some basic things which you should be remembering, because when we will go to more complex systems, so each and everything should be clear. So now I am assuming that there are some n number of particles, and let Fij, that is force on ith particle with respect to j, ith particle due to j. So this is read as force on ith particle due to j. For example, that is in this direction, and that is equal to minus times Fji. This is known as actually action reaction pair. So you will have seen that in, for example, books like NCRT and other stuff, they are what we have already concluded, like sum of Fix internal is equal to zero. So you might have seen that they are doing something like this. They are saying that F force on ith particle due to j is equal to minus F of j due to I. And then they are summing this up and saying that see, the net internal force is zero. But I have not done that. Uh, Else, what I am doing is I am just saying that the net internal force acting on some particle is zero. But there is difference what I am saying and what have been done in our books, or what have you previously read. The difference is that we don't know if we have n number of particles, we don't know what is the individual force which is being experienced by this ith particle due to the jth particle. We don't know. There is some interaction going on between the particles and we don't know what is the force. For example, if there are individual force, individual two particles only, we know, for example, there is some force interaction between the two. But when there are n number of particles, we don't know how that force changes and what is the internal force due to the each particle. But for sure we know one thing: whatever the forces are acting and how they are interacting, the sum of the internal force will always be zero. That is why I have defined it like that. So now what I am saying is that Fi, that is force on this ith particle. So force on this ith particle will be force due to this particle, due to this, due to this, due to this, due to this, and due to this. So this Fi is equal to summation of force on I due to j, where this j can run from 1 to n minus 1. I have made a mistake because I will not be included itself. So this is actually j equal to 1 to n minus 1. So, and j cannot be equal to I. This is the constraint on this equation. And you will be summing this f due to F on I due to J, plus there will be some external force which is not being applied by these particles. That is external to the system. And for each of the particle that may happen. For example, on this, there will be some external force. I have denoted that Fi external. That is the external force acting on this ith particle. And and uh, else that there is acting the force due to jth particle on I. And I am taking all those forces due, by this summation. So the net force on the ith particle is given by this equation.
Sir,
Yeah.
some summation of Fij is the external forces on I due to all the remaining particles. Then what is the Fi external?
What can you repeat?
Sir, Fij is the net
Yeah.
force on the
It is not the
ith
net.
particle due to the
Due to
not
due to
net, sir, not net,
all the remaining.
due to all remaining particles.
Yeah.
Then what is this Fi external? Fi external is due to which agency?
Fi external is something which is not included in the system. You have defined your system as n number of particles. But this force which is acting on this ith
Okay,
particle,
okay.
that force is not
I
being
got it.
applied. Yeah. That may be something gravitational or maybe some electromagnetic force, something else which is not due to these n number of particles. That is why I told you that it depends upon the system, how you define your system. For example, if you are defining your system as these three particles only, then the force which is being applied by this particle on that, then that will be external. Yeah. So
Yeah,
depending,
yes, sir.
the external and the internal are totally dependent on the definition of the system. Okay.
System, yes, sir, yes, sir. Yes, sir.
So Fi, that is the net force vector sum of all the forces on ith particle, is given by this equation, where I is not equal to j and j is running from 1 to n minus 1. So
Sir,
now this,
what is the essence? So then what is the essence of saying that the internal forces summation of internal force is equal to 0?
yeah, we will see what that means and how we will be going, how we will be utilizing that thing. Wait a minute.
Okay.
So what is now Fi? This is the net force on this ith particle. It includes the internal force and it includes the external force. This is the net force which is acting on the ith particle. Now, if we want the net force on the whole system, so we need to add this Fi for all the i's. That is what I am doing. F total on the whole system is equal to summation of all these Fi's. That is summation of all the net forces on the individual particle. And I am summing this from 1 to n. This will be from 1 to n because it will include the whole number of particles. Now, instead of this I replace this Fi by this thing. So this Fi is this thing. And then summation of Fij running from j equal to 1 to n and I running from 1 to n. So this thing is nothing but it is taking all the possible combinations of internal forces, and that we know is by definition equal to 0, isn't it? Are you getting this term?
It's
This is summation of
summation of
Fi due to
I
j.
is equal to 1 to n into this summation of j is internal force.
So these are all internal forces.
Yes, sir.
So this term represents all the possible internal combinations of the forces, and that the summation of those things will be zero. This is from the definition.
Sir, can can I say that, sir, this summation of I is equal to 1, I is equal to 1 running to n is actually actually includes the ith particle also. That is why the internal force is 0.
What?
When we say that summation from I is equal to 1 to n, it also includes the ith particle.
Yeah, it includes all the particles.
All the particles, its particle. That is why summation of all internal forces is then.
Yeah, that is zero. If we miss only one particle, then the summation will not be equal to zero. Because what the postulate says that summation of
That will be the
all
that will
the
be the
internal.
that will be the yes, sir. That will be the external force on that its particle. I got this, sir.
Okay,
I got it.
so this term is zero, and now there is summation of 1 to n fi external. That is this thing. So now we are left only with this thing. So the F net force acting on any system is nothing but the summation of the external things on external forces on. So we need not to worry about what is going inside, because the net external force on the system will be F external total only. Is this clear?
Yes, sir. Yes, sir. It is clear.
Okay. So now we will be defining a very important concept which is known as center of mass. After dealing with forces, now we will be defining this thing, because this is a very fundamental thing when we are dealing with the rigid bodies and extended bodies, or with the n number of the particles. So this is basically the center of mass, and this is a point. This is point in space. I have denoted this as G, and symbolically I have represented it like this. And the position vector of that G with respect to O is RG with respect to O. And we define this RG, that is the position vector of the center of mass, as summation of MIRI. That is, if you take this ith particle, you take the position vector U. Actually, what you are doing by this thing, you are calculating the mean of these position vectors weighted by their masses. This is the weight mean of position vectors, and the weights are masses. So this RG is this is how we define the center of mass. But the best thing is with this center of mass is that this doesn't depend on the coordinate system you are choosing. For example, you have chosen this coordinate system, and this is the system. For example, M1 is here, M2 is here, M4 is so on, and this is the configuration of your system. And now you have chosen this as your reference frame, and by choosing your reference frame, you are utilizing this formula. You got your center of mass here. Now, for example, you have same system, same configuration, but now you have something frame like this. And now see, R1 will be different, R2 will be different, R3 will be different. But when you will calculate this thing, you will get the same point. Obviously, you will get different RG, but the point will be same. That is, the point will be here only. That is why we are saying that this G is objective in nature. That is, it depends upon these articles only, or the objects only. It doesn't depend upon the frame. And it seems very trivial, but it is not. The thing is that you define something like this You have some Ri vector, you multiply it with mass. You don't think at it as a mass, but think like you have some vectors, you have one vector, you have another vector, you have another vector, and you are weighing those vectors by some scalars and then dividing by the summation of the scalars, and you are getting a point. That point doesn't depend upon the frame. uh, I will insist you to, like, can you formulate a formula like this? Like we have a formula summation of MIRI divided by M dot. And this is invariant to the frame you are using. You can use any frame. Can you formulate some formula like this? For example, can you MIRI square divided by M dot and see if by that you are defining something which is object. So you can play around this. Maybe you will also get something. But to make emphasis on this point, I am again saying that this center of mass is something objective and not depending upon the frame of reference you are using. So now for each particle, we can use the Newton's second law, that is Fi, that is the net external force on ith particle, which will be including the internal forces due to other particles, and the external forces on the ith particle is equal to mass of the ith particle and the acceleration of the ith particle. And F total of the system is nothing but the summation of such kind of forces, and which is equal to summation of Mi Ai. But we know Fi can be written as Fi internal and Fi external. So taking the summation and substituting this thing here, taking the summation, we can write summation of I to 1 Fi internal plus Fi external equal to summation of MIRI. I have just substituted this thing here, and rest is this. Uh, Now, summation of 1 to n Fi internal, by definition, this is 0. And Fi external, that is summation of Fi external, is equal to summation of MIAI, I running from 1 to n. And F summation of I to n Fi external is nothing but F external. That is the net external force acting on the system is equal to summation of MIAI. And AI, we can write AI as the derivative of Vi. Since Mi is constant, that is the mass of the ith particle is constant, because we are dealing with the velocities which are much smaller than the speed of the light. So there is no decrease or increase in the mass. That is, we are not including the relativity concept here. We are dealing with the classical mechanics. So Mi is constant. I can take this derivative outside. So this is d by dt of summation of Mi Vi. So think, you can see m1 dv1 upon dt, m2 d2 upon dt, m3 d by dt upon v3. Then you can take this m1 inside, you can write d by dt of m1 v1, d by dt of m2 v2, d by dt of m3 v3. And that is nothing but this, d by dt of summation of this thing. Is it clear?
Yes, sir. It is clear, sir.
Okay. Now what is now we define the summation, that is MIVI summed over all the system as L, capital L vector.
Momentum, sir.
And this,
Momentum,
this
sir.
is
Yes.
known as linear momentum of the system. Linear momentum of the system. If M1 V1 is the linear moment of first particle, then we can say it is the actually the summation of all the linear momentas of all the particles, and it is a vector sum, and that is defined as the linear momentum of the system. So F external is nothing but dot of this linear momentum. Okay, further we can see that this L by definition is nothing but summation of one I running from 1 to n mi See, Vi can be written as dRi upon dt, where this Ri is nothing but the position vector of ith particle related to the origin. See, you should not lose the track of the denotions. The Ri is the position vector of the ith particle related to the reference frame, and this is the linear momentum. And similarly, we can take this d by dt out, and then this is I running from 1 to n MIRI. Now we define this thing. Summation of MIRI, if you go back, see MIRI, we can write this summation as RG times M tot, where M tot
RG
is,
into M total, yes.
yeah. So I have written this as RG times M tot. So our L is nothing but d by dt of M tot RG. This is by the definition of RG. Okay. So coming back to this, F external is L dot. That means F external is L dot. L is nothing but so d by dt of L, d by dt of L is d by dt of M dot Rg, d by dt of M dot Rg. So F external is, we take this M dot out because this M dot is the total mass of the system that is constant. And then this becomes second derivative of Rg. And second derivative of Rg is nothing but the acceleration of Rg. So F external is m dot ag. So we started with the n number of particles, and we know that we have to write the second law of motion for each of the particle. And you, if you were dealing with the like n mole number of particles, so you have huge number of equations there. But now we have got something which gives us a bigger picture. We just need to know the external force, that is the, and this is actually the vector of external, that external force, and we need to know the total mass of the system, and we need to know the acceleration of the system. So this is what we were thinking we should be getting from this. And I'm again saying that this
This
is,
is only for sir rigid body, sir.
no, where I have made the assumption that it is a rigid body. I have used n number of particles. They may be moving around. They may be decreasing the particle distance may decrease or increase. I have never made any assumption that it is a rigid body. Yeah.
I am saying that, sir, can we apply this equation for rigid as if we have a rigid body, we can compute
Yeah.
the
Definitely.
center of mass and then
Yeah.
acceleration of the center of the gravity. That's the center of the mass, center of mass and velocity, and we can use this equation.
Yeah. So basically, each extended body is actually the n number of particles, where the interparticle distance is constant. So there is one more constant equation which we will be utilizing. Okay. So, but this equation f external is m dot ag. This is a general equation which is applicable for all kinds of n number of particles. Those particles may have constant interparticle distance, or they may be changing the shape, the extended body may be deformable, other things. So this is a general uh, formula which we can apply. Only thing which I want to emphasize here is that this F external is net external force acting on the system. So think you have some system, and whatever is coming outside from the system, you have to consider only the summation of that thing, and that you will put here. And this m dot is the net mass of the system. That is, I should not call it as net mass because it is not something which is vector and which will be adding and subtracting. I should say it is a total mass of the system, summation of the individual masses. And then we have the acceleration of the center of mass, which we have defined. And that too is the objective in nature. Okay.
Sir,
So
when we apply this on the deformable body,
yeah.
doesn't the sir center of the mass changes as if we integrate the deformable body in two parts, and the center of mass will shift. But you actually say that already say that it is an objective, that is the position of the position of center of mass will change, but the that point will be fixed.
No, no. What I mean, given you have these individual masses fixed, you have M1 here, M2 here, M3 here, M4 here, M5 here. Hello?
Yes sir, yes sir,
Hello?
yes, sir. Oh yes,
Okay. Is my screen visible?
yes sir, it is visible.
Okay. What I am saying is that given M1, M2, M3, M4, Mn, so this configuration is fixed, then the G point will get fixed. So it depends on these M1, M2, M3, M4, the configuration, where the M1 is, where M2 is, where M3 is. It depends on that thing. But it doesn't depend upon the frame of reference. If you choose for, you have given configuration of the system and you choose some different frame of reference. Now you will think that, okay, now I have changed the frame. This center of mass will be now here. No, it doesn't depend upon the frame of reference. Only it depends upon the configuration. If you change the configuration, the center of mass will change. I am not saying that. So if you have a body which is deformable, obviously the center of mass will change its position.
Yes, yes, that was my point, sir. That if we have a deformable body, the position of the center of mass will change.
Change, obviously. Even for this n number of particles, even if this is a rigid body, if these masses are moving, the center of mass will move. It will not remain here,
Yes,
isn't it?
sir.
Only thing
Uh,
what I am
okay. Yes, sir.
saying,
Then there is
this is something which we are defining, and the beauty of this definition is that the point corresponding to which this vector corresponds, that is something which is fixed in space, that is fixed in space and is determined totally by these configuration of these masses and not by this frame of reference. You choose any frame, this point will be fixed till these masses are fixed. When they change, they will determine where this point should be. Okay.
okay, sir.
Okay,
Done.
so finally we got this equation. F external is m dot ag, where this F external is the net external force acting on some body which you are considering as the system. See, you are taking some body as the system and you consider all the external force acting on that body as this F external. You are not bothering about the internal forces. And then m dot is nothing but the sum total mass of that system. And acceleration of, only you are considering only the acceleration of the center of mass, which is just a single point. So you have considerably relieved the problem. You have decreased the complexity of the problem. Now you have only this equation which you will be solving. Okay, so we will be using this thing once we get to the, once we will be solving the problems related to the extended bodies. Okay, let me first check some chats are there. Maybe someone is trying to join and I am not. Okay, no one is joining. This is great. Okay. Uh, so is it clear?
Yes, sir. It is clear, sir. Crystal clear. No doubt.
So I will quickly go to the previous, if it works, if my MATLAB works, I will quickly go to the previous simulation and run it. And to the so it may take time. Let's wait and see. So is till okay, it has started.
Start. This previous animation, sir.
Yeah, yeah, this is previous animation. Okay, so okay, it was running, but let me stop it. Or should it run? Okay, this is so let's change some. Uh, so you first see, you can see that this body starts from here and it goes around. This blue one is the Earth, and this is the satellite or some object,
The
and this is
light. Light.
yeah. So you can see it is following a circular path, isn't it?
Yes,
It is
sir.
following. This is a two-body problem, and I have simulated it. I have in last lecture I told you how it is working. But now let's change something. I will change the initial conditions and you will see what are the importance of the initial conditions. Okay, these are not just the values which we put. You are seeing those as the numbers, but how impactful they are.
Numbers.
Yeah, you will see when we change it
Maybe
here.
sir, maybe the path will be looks like elliptical, or first it will increase speed and then decrease.
Yeah, yeah. So I will change the perturbation. Let me take the perturbation as 300. Okay. So this is actually the perturbation I have given to the velocity. So initially I was giving the velocity in such a way that it moves on, it corresponds to the circular path. Now I have perturbate. I don't know. I only know that this velocity doesn't correspond to the circular track at this position. I have given more velocity and then it goes by itself. And you can see that it has followed a elliptical
Some
trajectory.
sort of elliptical path.
Not
Elliptical.
sort of, it is elliptical path, isn't it?
Yeah,
So
elliptical.
the
Yes, sir.
yeah, this is elliptical path. And this Earth is at the center, at the one of the forks of this
Okay.
ellipse.
Yes.
Yeah,
Yes.
we can increase this perturbation and see we can get
50,000.
more
5,000. Okay.
more eccentricity in the path. See,
Now there is
this is known as the perigee, which is closest to the Earth.
what 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 sir? Repeat.
This point, which is closest to the Earth, is known as perigee, and this point, which is somewhere here, that is known as apogee. These are the terminologies we use. Yeah. So actually, I have simulated for lesser time. I can increase the simulation time, and let us take maybe 5, and let us take the animation speed as 2000, and we have to increase the limit for
Frames. X
axis
axis. Yes, limit also.
axis limit and y axis limit, so that you saw that the animation was some, or not all the animation came in the frame or the picture.
Frame.
So we will be increasing this thing, and let's make it as 30. This as 30. This is not 30. You can see this is not 30. This is actually 30,000 kilometer. Yeah. I have multiplied thousand, so it is
It is
okay.
a yes, sir. It is multiply. It is multiplied by 1,000. It
Yeah.
is starting from Earth.
It is not starting from Earth. Actually, what is
Actually, it is
the size of
above
the size of the frame? See, it's not because of that thing. So you can see the eccentricity has now increased. Eccentricity of the path.
It is at the one
The
focus.
beauty of this thing is that this approach, this numerical approach, you know, you have applied the gravitational law. You have applied the gravitational law, and you have generated the differential equations, governing differential equations of the motion. You put it in the MATLAB and you simulate it. And by simulating the solution which you got after integrating, you saw that the path is elliptical. Now, there are some methods, analytical methods, by which you can show that indeed the path is elliptical. But see, those analytical solutions are not so simple. You can check out. That is not the purpose of this course. But you can check out that those are not so easy to show that this is the elliptical path. You can go through that analytical solution, which I will not be doing here. But in order to appreciate this thing, that you are simply writing the differential equations, giving these differential equations to the MATLAB, and your job is done. But it is not like that if you are analytically doing this thing. Okay, are you getting?
Yes, sir. Yes, sir. This is the graphical view of the and by numerical method, it is very clear to show that it is elliptical path or anything else.
Yeah. So I am showing the whole uh, code so that if anyone among you are interested, he can copy this code, write down on your in your PC and simulate the things and play with it to get something new. Okay, I think we are running out of time. Uh, so I will stop the recording. If you have any question, you can ask.
You start the recording.
I have stopped
Stop
recording.
recording.
Yeah.
Stop it.
Yeah. Yeah, I have stopped. Is it showing?
But start recording.
Yeah. Hello?
Four